In this tutorial, we're going to use the custom circuit methods to simulate the coherence estimates of 0 pi qubit. The notebook is based on this paper. I have linked the paper in the description and you can directly check it from there. Start with the installation. First, you have to check whether the Python version you have is up to date or not. You will need a Python version which is 3.7 or more than that to run scQubits. I have mentioned all the required libraries which you are going to use in this simulation. I've also linked the Google Colab link of this notebook, which you can directly copy from the link I have provided in the YouTube description box. Next, we have the GUI of scQubits. If we are using this notebook as a local Jupyter Notebook, then you can directly use the GUI and see how it goes for the scQubit. But as I'm using the Google Colab and it doesn't support the GUI, so I'm going with the old-fashioned CLI methods. If you want to see how the GUI looks for the scQubits, I have given a link in there which you can directly see. And this is how the interface of GUI for the scQubits looks like, where you have the choice for using which type of qubit you are going to use and what type of transformations you are going to use on the qubit and all the other parameters you are going to use. Let's start with defining the 0 pi qubit. Now, as the definition says, this kind of qubits exhibits rudimentary form of topological protection that combines exponential suppression of noise-induced transitions, which are the dissipation transitions, with exponential suppression of dephasing. So there are lots of jargons in this, but if I say it kind of in a layman terms, it's basically saying that it gives a topological protection against the bit flip and the phase flip errors, which are common in the transmon qubits, which we have. So this is kind of an upgrade from that kind of qubits. If I look at the circuit of the 0 pi qubit, I have taken the screenshot of this circuit from the paper which I've mentioned earlier. So you can see that it consists of 4 nodes, 1, 2, 3, and 4, and it consists of 2 linear inductors, L1 and L2. It also consists of 2 capacitors, which are C1 and C2, and a pair of Josephson junctions, which are mentioned by EJ1 and EJ2. Here the CJ1 and CJ2 are the Josephson capacitance, and it's basically saying that the two junctions have their own capacitance. I will later discuss that because of this capacitance and the other capacitance and the inductance, we have some kind of coupling errors which gives rise to the zeta mode. There are two challenges which need to be tackled by the design of the 0 pi qubit. One of these is to simultaneously realize large superinductors, large shunting capacitors, and high junction energy with very low state capacitances. So what it is saying is basically in the circuit we are going to use L1 and L2 such that they are very high values. We are going to use shunting capacitors for C1 and C2, and we are going to use the junctions the two Josephson junctions J1 and J2 such that they have very low state capacitances. And there is another challenge which need to be tackled, and that is the circuit elements to be pairwise identical to prevent coupling of qubit to a spurious circuit mode or the zeta mode. So what is this spurious circuit mode? So it is basically a kind of an undesirable noise which we have in the circuit, and it needs to be eliminated to have a better kind of result. Now, as the zeta mode is a fully harmonic mode, it means that it doesn't bias the junctions. So using generalized flux variables phi, now we can introduce variables theta and capital phi, which forms normal modes of linearized and non-disordered circuit. And we can write the equations as such as mentioned in here, where we have all the three parameters, that is the capital phi, theta, and theta. But we are going to eliminate this zeta and this sigma values, because sigma mode doesn't bias the junctions as we have known from here, and sigma is also cyclic and is decoupled when we consider the circuit. So these two modes are ignored, and we are left with only the capital Phi and the theta modes in terms of the generalized flux variables, right? And now we can create the circuit. So I have taken the parameters from the paper. So from this parameter list, we are going to use the set one, and particularly this column in the units of Planck's constant and gigahertz. And we have all the values for EC, ECJ, that is the capacitance energy of the Josephson junction and the Josephson energy, and we also have the inductance energy values. Now we're going to import the necessary libraries which are going to need to simulate the qubits. Um, so these are the necessary libraries, and using the custom circuit method, which is newly introduced in scQubits, we can define the qubit, uh, particularly this 0 pi qubit as such. So if you look clearly, this contains all the branches as in terms of the nodes as mentioned as 1, 2, 3, 4, and all these values basically saying what kind of um, circuit elements are in use. So J for the Josephson junction, L for the inductance, and C for the capacitance. And these values, EJ, and these values are taken from this parameter set for respective of their values. And now we can also look at the circuit, which basically is saying all the nodes which are present. And as we can see from this circuit and this representation, we'll see that the Josephson junction is present in between the first and second node and the third and fourth node, and it's mentioned as such in here too. And similarly, the other circuit elements, that is the inductance and the capacitances, as in 2, 3, 1, 4, and 2, 4, and 1, 3, are also mentioned in the defining stage of the qubit. And I have named the qubit as the my qubit. And if we take another type of definition for defining our zero qubit, it is as such. We can directly call the attribute of the method as qubits, and we can define all the parameters as in grade terms. So we can write the EJ values, the energy of the Josephson junction, energy of the inductance, and all the related values. We can also define the flux in here, which is present as in the external flux in the circuit. But we are going to use this type of definition as we are using the custom circuits. So you can also try this out meantime. Now, the scQubits basically uses the units in terms of the gigahertz, as you can see from this parameter set. So if you run this code, you can see directly that it shows the gigahertz. So it's the default unit the scQubits run in, but you can also change their unit to megahertz using this type of command code, and it will change to megahertz. And if you check it here also, we'll get it in terms of the megahertz too. So we are now changing it back to the gigahertz, and you can use it from there. Now let's take in consideration the Lagrangian and Hamiltonian of the circuit, which are basically the methods for its quantization, and it's also required for calculating the eigenenergy values and the potentials in Hilbert space. So first we are to use this Lagrangian. We are going to create a circuit object, and we can create it as such. That is 0 pi equals SQ, a method for circuit. I will name the qubit which I have created. In this case is my qubit. From file, no, it's not from any file. I have created directly in here, and it's also saying the use dynamic flux grouping, which I have mentioned as true, and generate noise methods. So what are these? So the generate noise method is basically a Boolean argument that determines whether methods for estimating coherences are generated for this object, and dynamic flux grouping is kind of a Boolean argument that determines if a flux grouping is there or not. So we're going to use the 0 pi object in later for calculating any kind of uh, results for the qubit, which you have mentioned earlier in here. So to calculate the Lagrangian, we can directly call the method sim Lagrangian, and it will show us the Lagrangian for the circuit in terms of phi. So what are these phi values? That is phi 1, phi 2, phi 3. So if you see the earlier definition, we have defined the modes capital Phi and theta in terms of flux variables, that is phi 2, phi 3. And that too, these values are also mentioned in terms of the nodes, that is phi 1, phi 2, phi 3, phi 4 for the 1, 2, 3, and the 4 respective nodes. So using this sim Lagrangian method, it calls the Lagrangian in respect of the nodes which are present in the circuit. And if we want the Lagrangian in terms of phi and theta, we can change it by using this parameter, that is vars type and equals to new. If we write, then we'll get it in terms of theta and phi, which is basically the general terms. This mapping from phi to theta is done using a matrix M, and if we run this code, that is this code, then we can see what this matrix M is. So if you run this, you will get this as an 4 by 4 matrix with these value elements. And using this transformation, we can directly get the values of theta from the phi, which are the node variables. Now, as we considered a disorderless case, so we are only left out with the phi and theta degree terms to form the Hilbert space of the qubit. And as we generally write the Hamiltonian of the circuit as the Hamiltonian for the 0 pi qubit plus the Hamiltonian for the zeta and the internal Hamiltonian. But as we are considering that the zeta mode is decoupled in our circuit, and we are also going to ignore this internal Hamiltonian. So in this case, we're only left out with this 0 pi Hamiltonian, and we are only going to use this to calculate the total Hamiltonian of the circuit. Now, as I have mentioned here too, the zeta term actually arises due to the coupling from disorder in the capacitance value C and the energy value of inductance EL. Uh, Now we will calculate the Hamiltonian in terms of the transform coordinates theta I. Using this method, we can directly get the expression in terms of the theta i's for the Hamiltonian of the system. So as you can see, it contains the terms Q and 1 and G. So what are these values? So the Q terms you are seeing are basically the extended degrees of freedom. The N 1 and these terms are the periodic degrees of freedom, and the Ng values are the offset charges which are present in the system of the qubit. And the phi value which is mentioned here, it represent the external flux which is present in the circuit, as it can be seen from this here. Now, we can change the values for the phi1, that is external flux, and ng1, that is the offset charges, by directly calling these attributes and then changing the values with this. So the value for 0.5, 0.6 for phi1, and the ng, that is the offset charge, are the default values, and we are going to use that only. Now, these units are basically in the units of 2 pi. So we can calculate the Hamiltonian in the vector form too, using this method. And if we see the output, it is basically a compressed kind of a matrix which is present, and we are not able to see it in here, but it directly returns the value of the Hamiltonian as a matrix form. Now we can get the values of the Hamiltonian. Now we can calculate the eigenvalues for the Hamiltonian using this method, eigenvals. So if we output the value, we'll get the all the values, that is the eigenvalues for the Hamiltonian, which I have just mentioned in here. And these eigenvalues are actually required if we are going to represent the qubit in terms of the energy spectrum values, which you are going to see in the visualization. Now visualize all the values which are going to be mentioned here. It is recommended that you import the numpy as np, because I have used np name or all the numpy parameters I have used in the circuit. So I imported the numpy as np, and then this call method basically is saying that plot the eigenvalues as per the parameter values for this type of range. Now the phi1 is basically saying that I'm going to use the parameter the flux, and I'm going to plot the values of eigenvalue uh, versus the flux values. So if I output this, we're going to see such kind of diagram. And as you can see, the y-axis represent the energy in terms of the gigahertz, and these are the values of phi1. And if you see, there are these lines which are represented here, and all these lines represent the eigenvalues which we got earlier using the eigenvalue called eigenvals method. And these are the values which are represented in here for this range of numbers, as you can see. Now we can also plot the potential, and for that we're going to get the expression for the potential. As such, we'll call this attribute, that is u pi potential symbol, and then we'll get the values, the expression in terms of the theta as such. And we can visualize the potential using this theta1, theta2, and theta3. So what are these theta1, theta2, theta3? Are basically the degrees of freedom which are going to be used to represent the potential. And we have set the values of theta2 equals to 0. As such, that will get only a two-dimensional plot. So if we put this code, we'll get to see this kind of potential energy versus the theta, that is the degrees of freedom graph plot. And these values represent all the potential energy in gigahertz terms. So you can directly visualize the potential of the qubits as such. Now, if you want to plot the wave function for the 0 pi qubit, you can directly use this method with these parameters, and you will directly get the wave function, as you can see from here. And this pi theta 3 mod square is basically saying the probability. So these are probable values which we get from the wave function. And theta 3, as mentioned earlier, is a degree of freedom to represent the qubit values. Now let's have a look at the noises which are expected while we study the qubit, that is 0 pi qubit. And to identify the most damaging noise channels of the 0 pi qubit, we can calculate and compare various depolarization and dephasing rates that originate from coupling to different noise sources. And while considering the noises, we have one assumption is that the different noise channels we talk about are uncorrelated, which means that taking into consideration of one noise channel doesn't actually affect the other noise channels. So the two particularly most influential noises, that is the dephasing noise and the depolarization noise, we are going to consider in here. So what is a dephasing noise? That is represented by the value d5. So it's one of the ways through which the system loses its coherence, and as you can say, it's one of the decoherence methods. And in this type of noise, relative phases associated with superpositions of multiple states are lost over time. And as we can see, it is also denoted by the value d5, and it defines the time needed for a quantum superposition to turn into a classically mixed state, or losing its all coherence from the quantum state. Now there are different kind of dephasing noises. This one of the most important is the 1 by f noises, and it leads to the slow fluctuations of the energy levels spacing, which results in the dephasing of the qubit. Now why do we write this as 1 by f? So as the empirical evidence shows, the superconducting qubits are typically exposed to multiple noise channels with approximate 1 by f spectrum, and because of that we have this name 1 by f noise. We can now write the spectral density as such in terms of the value s, which is a function of omega, which is the noise channel frequency, and it is written as twice by a lambda square or upon the mod value for the channel noise frequency, and where is a lambda basically the amplitude of the noise channel lambda. And from this we can write the dephasing time as such, that is 1 by t5 equals square root of 2 a lambda del omega 01 divided by del lambda, and under square we have this L terms, that is omega low and t experimental. So what is this, all the terms represents? So basically we have seen the A lambda, which is the amplitude of the noise channel lambda, and this value, that is omega low, basically represents the low frequency cutoff of the noise channel. The t experimental is basically saying the experiment time we are going to conduct, and as you can see the default values which we are going to use in here. We can also change the parameter for the amplitude term as using the A noise inside our method, which we are going to use it directly over our qubits. Now in case of the 1 by f noise, we have different type of noise methods. One of them is the flux noise, and it is due to the fluctuations of magnetic flux in the enclosed loop by the two junction, and treating the phi external as a noisy parameter of the lambda, which is our noise channel. And while we are using this, if we call this method over our qubit, 0 pi qubit, we are going to get this value in terms of order 10 power 19. And if we see the definition, we are getting the value for the 1 by t5. And if we want to get the value for t5, we can directly introduce one parameter, that is get rate, and we can directly write true, and then we will get this value in terms of nanoseconds. Now this default A noise for this 1 by f flux noise is 10 power minus 6, which is the phi naught as mentioned. Now there is another type of 1 by f noise, which is the charge noise, and it is due to the noisy voltage sources capacitively coupled to the nodes of the circuit. Then we can directly also call it over our qubit, and in this case our A noise is also 10 power minus 4 in terms of the value E, which is the electron, and we can also use the get rate value to true in this method, so that we can get the value in terms of the nanosecond. And we also have this another type of noise, which is the critical current noise, and it is due to the trapping and de-trapping of charges at defect sites inside Josephson junctions, and it can also enhance or suppress tunneling across the junction, which leads to the fluctuation of the critical current in the circuit. So I can also use this method, that is d phi 1 over FCC, which is the CC for the critical current, and we have the E noise in this case as 10 power minus 7, and it is denoted by IC. If we output this value, we'll get this kind of value for our defined qubit. And there is another kind of noise which we didn't mention here, which is the short noise, and it is due to the thermal excitation of the zeta mode. And as we have already ignored the zeta mode, we can also ignore this short noise in our case. But in case of the ideal conditions, we cannot directly remove this kind of short noise and also the zeta modes. But for our simulation purposes, we have not considered zeta mode, as it will be more complex. Now let's talk about the depolarization, which is denoted by T1, and it is due to the process associated with a spontaneous transition between energy eigenstates. Now in scQubits, we will use the standard perturbative approach or the Fermi-Golden rule to get the transition rates. We can write the expression for the transition rates as such, and we'll get this kind of expression where the value b lambda represents the noise operator, and this s is representing the spectral density function, which is a function of the omega, which is the frequency for the noise channel. And if we see clearly, this term, which is represented in terms of the mod, represents the expectation value for the noise operator, and while we multiply it with the spectral density upon the reduced Planck's constant square, we are going to get the transition rates, as we have taken into consideration the Fermi-Golden rule expression. Now there is one kind of depolarization noise which we are going to consider here, and this is the flux bias line. Now this depolarization effect is due to the current fluctuations in the circuit, and it can be represented by the spectral density as written, and here there are new terms such as the m, the hyperbolic chord function, and the kb values, and the capital T. So the kb, as we know, is the Boltzmann's constant, and we are taking into consideration the value m, which represent the mutual inductance between the qubit and the flux line, and the capital T represents the temperature in Kelvin. So we know all these parameters, and we have the default values for them, and we can directly represent the transition by choosing the indexing using these values, that is I and the j terms, and then we will get the flux bias line error, as in the depolarization error noise in the particular qubit. Now if we run this method, T1 flux bias line, for the flux bias line depolarization, we are going to get the value in terms of 1 by T, which we get is this, and this in the order of 10 power 42, but as we know it's in 1 by T, so if we write as get rate equals to true, we will get it in terms of the nanosecond. Now there are other some parameters which you can directly play with using this table, and you can also change the default values and see how the qubit behaves. And particularly there is one parameter, that is the total is default in true, and it basically says from where to where the transition is happening, And if this total value is set to false, it means that the transition is happening from I to j. But if it is true, then it is basically combining the effective depolarization time of both j to I and I to j state, and we are going to get a result which is a combined average of both the transition rates. Now we can check the effective noise channels for the qubit using this command. So this command basically shows what are all the effective channels of noise we can use in the qubit which we have defined. Now when we run this, we'll get to see this type of an array with all the names of the methods which you can directly call on your qubit to apply the noises. So these are the T5 flux over FCC, the direct flux, the charge noise, the capacitive, inductive, and the flux bias line, which is the depolarization we have just seen. Now, while considering this kind of noises, to plot the values, we basically sometimes consider the effective noises, and this effective noises is the total depolarization time. So we will get this kind of noise, but there are two type of effective noises which you can see from here. It is T1 effective and there is a T2 effective. So what's their differences? So the difference is that the T1 effective is basically the total of the depolarization time, and T2 effective combines both the total of depolarization time as well as for the dephasing of the pure dephasing of the qubit state, and we get a combined value for this. Now if we run this at T1 effective, we will get to see the total depolarization time, and this result is as such. And similarly, you can also use this gated method here too to get it in terms of the nanoseconds or the second values, and this is the T2 effective. And if we run this method, we're going to get this value, which is the combined effect due to the pure dephasing as well as the depolarization channels. And we can also directly use these parameters inside the method to call the necessary effective channels which we are going to use for calculating the T2, and the noise channels we have considered for this command is this, that is the T1 flux bias line, and this T5 1 over F flux. This dict parameter basically defines the noise E noise, which is due to the amplitude, and the defining of this method as in the parameter of the noise channel. So if we run this, we'll get this value as such. Now we are ready to plot the results of our qubit. So first of all, we are going to print the results for our coherence versus flux, and for that we are going to mention the plot parameters and methods, and you can actually mention what type of noise channels you are going to use for defining the plots for the coherence versus the parameter values. In this case is our phi1 or the flux. So in this way you will get two graphs as such, and the subdominant noise, which is in this graph flux bias line, it's showing that it doesn't contribute much to the coherence of the qubit, that is in our case is 0 pi qubit. Now if we don't specify any parameters for the noise channels which we need for our coherence versus parameter value method, then it is going to plot all the expected noise channels for our qubit. And in this case we have all this, that is d5 1 over f flux, d5 over f ng, which is the charge noise, and then we also have FCC, which is the critical current noise, and this all these required channels such as the capacitive. Also we have the inductive channels, but they are mentioned as some dominant noise channels because they doesn't contribute much to
the coherence effects of our qubit. Next, we have the T1 effective versus flux. As you have seen, the T1 effective basically means the depolarization effective. And if we plot the graph between our T1 effective versus parameter values, that is in our case is phi1 or our flux, then we're going to get a graph such as this. So you will see that this graph is not that much smooth because I have used the values in between minus 0.5 and 50, and the noise channel are this. So we will get the graph as such for the T1 effective for the two uh, two axis, that is the time axis and the flux axis. And this graph over here, which is d phi 1 over f flux, gives the relation between the dephasing time and the flux, which is also a coherence effect. So we get the graph as such. And now we can also plot the graph between T2 effective and flux. So T2 effective, as you know, gives the combination of both depolarization and dephasing noise time. So if we use this T2 effective against the flux parameter phi 1 for this set of values, then we're going to get a graph such as this for the T2 effective, for y-axis being our time and the x-axis is our flux. And if we also specify the parameters for the noise channels about what type of noises we need in our T2 effective while calculating, then we can also generate such graphs. And if you see, this is more smooth because we have directly specified what type of noises we're going to use and also defined a good amount of variables which is going to be used for calculating the phi 1 values. So we get the graph of a T2 effective as such, for y-axis being the time and x-axis being our phi 1 or the flux. Thank you so much for your attention. And if you have any doubts regarding the video, please comment down in the comment box. And for more documentation, you can check this web page by scQubits. I have also provided the link for this Google Colab in the description box, which you can directly copy and use as per your need of scQubits. And I will be seeing you in the next one.